Hello everyone. So in this case, we're going to be talking about a reaction that's called reversible reaction. So previously, like we have talked about, in this case, irreversible reactions. So the biggest example that I've given you was the reaction of carbon plus oxygen to give you carbon dioxide, and that was represented by a single arrow. Okay, single arrow meaning to say that all of this is going to react to create carbon dioxide. So we're going to have at the end 100, you're going to have none of this left. Hypothetically speaking, obviously, this is actually not quite true. And we're going to have 100% of this at the end. Okay. Now we have reversible reactions as opposite to irreversible reactions is actually shown by a bidirectional arrow. So that means to say it can go either way, and sometimes it's actually shown as well as the double hook. Okay, that is the same as this. And what it's telling you folks is if I mix nitrogen gas and hydrogen gas, some of those atoms are going to create ammonia gas, but then at the end, not all 100%, you're going to have a mixture of leftover nitrogen, leftover hydrogen, and definitely some ammonia. So that is actually what reversible reactions are. You actually have a mixture of products and reactants at the end. Irreversible reaction means you have no reactants, theoretically speaking, at the end, and all products at the end. Okay, so that's what reversible reactions is. Now, because of this, they are product to a phenomenon called equilibrium. And we're going to be talking about that at the end of this video. So reversible reactions can be expressed in an equilibrium constant, which is shown here. This is very confusing, so the best case is I'm just going to show you some example. And FYI, this brackets tells just you concentrations in molarity, and obviously we have not talked about concentrations in molarity yet. Okay, so here are some examples. So the reversible reaction involving nitrogen hydrogen gas that gives you ammonia can be expressed as you can see. Products is on top, reactants are in the bottom. Now, there are exponents. Where do these exponents come from? Folks, those exponents come from the coefficients from the balanced chemical equation. All right, so that is where those numbers come from. FYI, if there was a liquid or a solid in any of these equilibrium expressions, they are not written down in equilibrium constant. Okay, now why is this very, very important? FYI, this KCs or this equilibrium constant actually has a bearing for our class. So I'm going to erase all of these things. So what happens? So what happens if we have more products at the end? If we have more products at the end, Kc then is going to be greater than 1. Okay, so if we have more particles on top, obviously the particles on our top are the products, right? If we have more of those, the number is going to be bigger than 1. If we have more reactants during equilibrium, okay, what that means to say is our equilibrium constant is going to be less, okay, less than 1. Okay, and if you have equal amounts of products and reactants, guess what? Right, so that's actually a very, very important thing. So if I give you any equilibrium constant, okay, you should be able to tell me which species is dominant in this case. So we're going to go through a couple of examples. So let's say we'll take this example here, the second equation, phosphorus pentachloride gives you phosphorus trichloride plus chlorine gas. What happens? What if I tell you that the Kc of this reaction is, I'm just going to make a random number, 1080. I don't know why that number came to mind, but 1080. What does that tell you? That tells you that the dominant species at equilibrium, okay, is going to be the products. Why is that? Because Kc is bigger than 1. Okay? Now, what would have happened if I told you that at equilibrium, same hypothetical, that this Kc is, let's say, 0 0.0001. What's the dominant species? Well, the dominant species, folks, is going to be the reactant. And why is this? Because the number, the equilibrium constant, is less than 1. So the take home here, folks, is just knowing what species is dominant based on the equilibrium constant. If the equilibrium constant is bigger than 1, the dominant species is the product. If the equilibrium constant is less than 1, the species that's dominant is the reactant. And if it's equal to 1, both products and reactants are equal at equilibrium. FYI, small numbers less than 1 can also be expressed as scientific notation. So this can actually be written as 1 times 10 to the negative 4. So negative exponents in scientific notation is also an indication that this is going to have reactants that are dominant. Okay? I hope that helps. So why do we care about this, in this case, these reactions? Because there's a principle on equilibrium called Le Chatelier's, and all I want you to do, folks, is just, in this case, just read through this. Okay, this is self-explanatory. So if you increase the concentration, it shifts to the opposite side. If you decrease the concentration, it shifts to the same side, blah, blah, blah. Now, pressure, folks, is we're only going to be talking, okay, we're going to be talking more about if the gases are involved in this case, okay? So in the previous thing, increasing and decreasing pressure would actually have an effect on gas. Now, why does increasing and decreasing pressure have an effect on gas? Well, folks, how do you get gas, right? So if you have something liquid, right, in order for it to become a gas, it has to escape, in this case, the actual container, okay? If you put pressure, if you put downward pressure on the glass, it prevents the escape of these liquid particles into the gaseous phase, right? And that is why increasing the pressure decreases the amount of gas, okay? If you remove pressure, now these particles are now free to escape into the vapor phase or the gas phase, okay? And then increase and decrease temperature, we're going to be talking about that soon. So we might as well do an example here. So let's look at the chromate-dichromate equilibrium. FYI, so this species here, folks, is yellow. This species here, folks, is orange, okay? Water is obviously colorless, and hydrogen ions is actually colorless as well, all right? So this is at equilibrium. Now, let's say, okay, I'm just making this hypothetical. Let's say that the KEQ of this thing, or the equilibrium constant, I'm just going to make stuff up now, is 1 times 10 to the negative 2, which means to say it's 0.01. Okay? If you look at the number, folks, the number is less than 1. So what species is dominant at equilibrium? Well, in this case, the species, obviously, if you have an KEQ less than 1, the reactant side is going to be the dominant species. So in this case, at equilibrium, the color that we would expect to see from this solution is going to be yellow. Okay? And that is based upon KEQ. Very, very, very important. Okay? Now, what happens, folks, if we add water? If we add water, we are increasing the amount of water which is on this side. According to Le Chatelier's principle, it's going to shift to the opposite side. And guess what color is going to be dominant? If I add water, it goes to the opposite side. Where is that? The color that's dominant if it goes to the reactant side is yellow. So obviously, if I add water, this solution will remain yellow. Okay? What happens if I remove water? If I remove water, okay, what happens, folks, is if I remove water, and I'm just going to erase this very quickly, folks, so that there's no confusion. If I remove water, folks, if I remove water, it says the reaction will shift to the same side. If I remove water, what happens, folks, is this reaction is going to shift this way, right? Because there's going to be less, so it has to shift that way. What color will we see? We are going to see the color change from yellow to orange. Okay? What happens if it's orange if I add, let's say, let's say I add chromate solution. So I'm going to increase chromate solution. Again, if you add chromate solution to the reactant side, it's going to shift to the opposite side. It's going to become more orange. All right? Now what happens, folks, if I add the dichromate, this is chromate, this is the dichromate. What happens if I add more chromate? So I'm going to increase the amount of dichromate in this case. Well, again, it's going to shift to the opposite side. So obviously, it's going to turn from orange to yellow. Okay? So that is actually Le Chatelier's principle in a nutshell. Now, the wrinkle in this case is what happens if we add or if we heat the solution or we cool the solution. Well, we don't know in this case, folks. In this net ionic equation, heat is not shown. So we don't know if this is something that's endothermic or exothermic. So let's say I give you there's two ways that you can tell whether something's exothermic or endothermic. It's based on the energy diagram. This, folks, is endothermic. That is exothermic. So if I gave you an energy diagram for the dichromate equilibrium and told you that it was the shape, that means to say that heat is being released. So this therefore means to tell you that heat is on the product side. Exothermic means heat exits on the product side. If it was the opposite way, sorry about this, that means heat is going to be on the reactant side, endothermic. Exothermic means heat is on the product side. And again, you can tell by looking at the energy diagram that's provided to you. So that's one way. The other way that you can tell whether something is endothermic, exothermic is by in this case, the sign for Q. If Q is positive, that means it's endothermic. And again, if you recall, we calculated Q from ms delta T. We take the mass of something multiplied by the specific heat and the change in temperature. If the Q is negative, this is going to be an exothermic. So another way that we can tell that this is an exothermic reaction, if I gave you the Q for this reaction is 1,000 calories or 1,000 joules. That should tell you, the negative sign in front of it tells you that's an exothermic reaction. So two ways, either the energy diagram or the sign of Q. Okay, now what happens then if this is an exothermic reaction? Well, folks, then it's just a straightforward Le Chatelier's principle. If I heat this system, where is heat? Heat is on the product side. So if I heat this system, that means to say I'm going to increase the heat. This is kind of like increasing the concentration of products, which means to say it's going to shift to the reactant side. It always shifts to the opposite side. So therefore, this is going to go, if this was orange before, it's going to turn yellow. Okay, if I cool this down, which means I'm removing heat, right? If I'm removing heat in this case, that means to say that it's going to shift to the same side, which means to say that it's going to turn into orange color in this case. All right. So the take home here, folks, is in equilibrium expression, you just need to know, first of all, what are the effects of adding products or adding reactants, and you should know that adding something shifts to the opposite side, removing something shifts to the same side, and then heating or cooling it is dependent upon whether the reaction is endothermic or exothermic. Okay, and you can tell whether something is endothermic or exothermic based on the energy diagram or the sign of Q. If Q is negative, it's exothermic. If Q is positive, it's endothermic.